So this example is number 14 from the book, but I've put an asterisk there because I've modified some of the wording and I've added a part to the problem. So in number 14, we're given a population of currently that 200 humans, 200 bacteria, is growing at 5% per year. And the first part is to write a formula for the population P as a function of time T years from now. So P would be using this model. We would have P is going to equal 200. And then we have 1 plus R, and that would be 1.05 to the T. Okay, so here I've entered our model for the population of 200 and a rate of 5% per year and graphed it. And I also adjusted the settings so that we can see more of the picture, and I zoomed a little bit differently. And so here we can see that this curve looks similar to any other exponential. The only difference is how these tick marks are changing depending on what we're starting with and what we have 5%. But the exponential growth always follows this sketch of a curve. In part C, we're asked to estimate the population 10 years from now. When we do this, we're going to get the population is 200 times 1.05 to the 10 power. And when we plug this into our calculator or some other device, we get about 325.7789. Now, for populations, having a decimal doesn't necessarily make sense, and so you might round up because this is an estimate after all, or you might round down but think, well, we only have 0.7 whole things, we really only have 325. But for this problem, we'll round up. So the doubling time, what they're asking for in this case is when are we going to have a population of 400? So I could plug this in. Whoops. Like this. Or in any situation, sometimes you might even not have an initial population, and you're going to start with an initial population of 1, and then you're asked for when are you going to have 2 if your initial population is 1. Either way, if I divide both sides by 200, I'm going to end up with 2 equals 1.05 to the T. Now we want to solve for T. And this is where our knowledge of natural log is going to come in. We can take the natural log of both sides and that important useful property allows us to bring the T down front and then we can solve for T. We have a number equals T times another number. This is a number, even though we don't really know what it might look like without going to a calculator, that we can divide both sides and solve for it. So then we get the exact value is going to be T equals ln of 2 divided by ln of 1.05. And when we plug this into our calculator, we're going to get about 14.2067. So that's saying in about a little over 14 years, the population will double with this kind of exponential growth. In part E, we're asked, what is the continuous growth rate for this population? So what we want is we want that our population is going to be P sub 0 e to the RT, and that in this case it's 200, that this ends up being the same as 200 1.05 to the t. So the question is, what is this R value for the continuous growth rate? In some cases, that might be more meaningful than the percent per year. So what we do is we focus on the fact that these should be equal, and what we can do is we can use t equals 1. At any given t value, they should amount to the same population size. It's easiest to use t equals 1. So we can divide both sides by 200, use t equals 1, and we get e to the r should equal 1.05 to the 1 power. We want to solve for r. So again, this is where natural log will come in. Take the natural log, or ln, of both sides. And either using that useful property by bringing the r down front. So I'll write that down. We can write this as r times ln of e. And then remembering that that is the same as 1. Or recognizing that the natural log and the exponential are inverses of each other. So if you do one right after each other, composed with each other, in other words, you're back where you started. They're undue functions. You get, either way, you get r equals ln of 1.05. Again, that's the exact value. Going to a calculator, we get r is somewhere around 0.04879. So what this means is that the continuous growth rate, instead of 5% per year, the continuous growth rate is 4.879% for our continuous growth rate. Okay, so this is the curve our original 200 times 1 plus r to the t model, 200 times 1.05 to the x. And in part E, we found the continuous growth rate to be 4.879x. So the same model should look the same. And if you see, they are exactly the same. You can't tell the difference. They have the same curve. So it doesn't matter which one we use. We plug in 5 years here or 5 years there, we would get the same answer.